everyone, welcome to Unit 5. You started off in Unit 5 with a little intro to sequences and series, and so, or not series, just sequences. And so hopefully you got a little information about that today, and then we're going to talk specifically about one type of sequence, a geometric sequence, which we can also call an exponential function. So let's move right along. Exponential functions are the parent form of, or have a parent function form, f of x equals b to the x. And so b is the base. You can put that there. And they come when you multiply by the same number over and over, which is how it connects to a geometric sequence. Now, with geometric sequences, there is a horizontal asymptote where the graph will approach this value but never touch it at typically y equals 0. And then this doesn't have to do with geometric, but for exponential functions, we have two key points, 0, 1, that's our y-intercept, and then 1, b. So that comes from if I plug in 1 for x, I get out my base. Any power raised to the first power is itself. So let's look at a couple different scenarios. When b is greater than 1, then we are multiplying by a number larger than 1 over and over and over. And so that's going to be called growth because it'll be increasing. And then when b is less than 1, or between 0 and 1, negatives are different. When b is less than 1, then we're multiplying by a fraction over and over. And that makes each next number smaller and smaller, like you saw with some of the sequences that we've done. And so that represents decay because it's decreasing. With exponential functions, we can plug in any value we want. So the domain is all real numbers, and the range is going to be 0 to infinity because of that horizontal asymptote. Then we'll apply transformations, and everything will kind of change a little bit accordingly. So let's do a couple, or one graph, y equals 3 to the x. So first, with sequences, we always start at x equals 1. We're not going to do that anymore. This is a real graph. I will show you how they connect, though. So first thing we do is we'll plug in 3 to the negative 2. Remember, that's going to be 1 over 3 squared. So that equals 1/9. Or with a negative exponent, you move it to the denominator of the fraction. So with 3 to the negative 1, that'll be 1/3. 3 to the 0 equals 1. Anything raised to the 0 power equals 1. 3 to the 1 is 3, and 3 to the 2 is 9. I'll plot those points. So at negative 2, we have 1/9, very close to 0. Negative 1, 1/3, 0, 1, 1, 3, and then 2, 4, 5, 6, 7, 8, 9. And then this will just, if you know the pattern, think about the sequence, it will just keep going forever and ever. And if we keep going negative, these will just keep being 1 over 27, 1 over 81, and so they get closer and closer to 0. You can plug any value in, but you will only get positive values out, and you'll never actually touch 0. So make sure you notice that that's a parentheses, not a bracket. Now, because it never touches 0, then there is no x-intercept. The y-intercept is 0, 1. Asymptote, there's a horizontal one at y equals 0. And then we'll do some end behavior. End behavior is the limit as x approaches negative infinity. The function approaches. So on the left side, it's approaching 0, remember. And then on the right side, it's going to be approaching positive infinity. All right. So what I want you guys to do now is try the second one. You can pause the video and try it, and then check back to see how you did. I'll be working through some of it. Okay, and so for our end behavior, this time, hopefully notice that the left side, as x approaches negative infinity, the values are getting larger and larger because the negative exponent will flip the fraction. And as x approaches positive infinity, that is where it gets smaller and smaller, but never into 0. All right, this one is decay, decreasing, and the last one was growth. It was increasing. Okay, so let's talk about what to do when we have some transformations happening. So we're taking it all the way back to unit 1. We have y equals 2 times 1/2 to the x minus 4. So this is vertical stretch by 2 and down 4. Remember, the base is 1/2. That is not a transformation. It's the base of the exponent. So we have our 2 key points. What we like to do is make a table out of them. And we'll do 0, 1, 1, b in the table. And so then we think about all of these transformations. A vertical stretch by 2 happens to the y value. And so that means I'm going to multiply by 2. So what we do is we multiply all the y's by 2. And then down 4 also happens to the y values. It means I'll subtract 4 from all the y values. And so I do that next. 2 minus 4 is -2. 1 minus 4 is -3. And then what I'll do for my final answer, well, for my graph, is I will plot these or x values with these y values. So nothing happened to the x's. So I have 0, -2. I'm going to move this up a couple. Nope, move it up one more. Like that. And then I'll plot the graph. 0, -2, 1, -3. And then we have an asymptote at y equals -4 because it shifted down 4. So that was y equals 0 moved down 4. That's how I knew what to put there. And then this is decay. So the 1/2 is going to come up and have this shape. So the shape is really important. Now you know what they look like for growth or decay. The domain's always all real numbers. The range got shifted down 4. And the end behavior as the left side going up and the right side approaching the asymptote at -4. So I'll give you guys a second to look at all of that over. If I did anything too fast, then you go ahead and pause so that you can get it all copied down and look back over it. All right, we'll do this one together. We have another one with 1/2 times 2 to the x plus 6. So remember, b is 1/2. Then we have to make this proper. You have to pull out the 2 and rewrite it like x plus 3. And so that 2 is a horizontal compression, or it's opposite when it affects the x by 1/2. And then this is left 3. And so we will make our table. 0, 1, 1, B. But this time, everything happens to the x values because they're all horizontal stuff. So the first thing means I'm going to multiply by 1/2, but all of the x values get multiplied by 1/2. So that's 0 and 1/2. And then left 3 means all the x values move left 3. And so I'm going to move them to the left 3. That'll be -3 and -2.5. And then again, we plot, nothing happened to the y's, so we'll plot these values with these values. -3, 1, and -2.5, 1/2. Nothing happened to the y's. The domain never gets affected because it's all real numbers, but the range stays 0 to infinity. My asymptote did not move, so I can plot that like this. And then this has the same shape. It's decay because the 1/2 is less than 1. And so it's got that decreasing curve, which means on the left side, we're at positive infinity, and on the right side, we're approaching 0. So again, give that a look, pause, make sure you understand and see all the pieces, and then we're almost finished. For this last one, I'm just going to pick one that has two things going on, one to the x and one to the y. And so that one we'll do is this C. And so what we'll do is we'll just make the table. Well, let's first identify the transformations. This is a reflect over the y-axis. Remember, y on the inside and then up 1. So I'll make our table 0, 1, 1, B. The B this time is 3. That's the base, not a transformation. And then reflect over y-axis means multiply by -1 the x values because it's happening to the x. So I'm going to multiply these by -1. And then up 1 is something I'm going to do to the y values. So I'll go up 1, add 1 to each of those. Then again, I plot the finished product. This time it's a combination of the two. So we have 0, 2, and -1, 4. And even though this had a base bigger than 1, this time we have a y asymptote of y equals 1. It still has a negative decay because of the negative exponent. Remember, that could really be 1 over 3 to the x. Those are the same thing. So it's like 1/3 to the x. Okay, then let's just identify. We have the asymptote is at y equals 1. That's the last thing I wanted to do. Pause, make sure you understand how to graph that. We're not doing all of them, just that one was the only one I wanted to do. But you could look at any of the others in Desmos and see what they look like. Give them a try on your own. This last thing is just that e to the x is, this is a natural number that shows up in nature a lot. The base is e, and so e, when you have a positive rate of change or a negative rate of change, they still have the same properties as regular exponential functions. You can type e into your calculator. It's like 2.718 and then blah, 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 something like that. Okay, so you guys are going to check Canvas to see what else to do, and I hope you have a great day. Thank you so much.